All right, I think we have a quorum, so let's begin. So we left off last time by talking about the start of the explosion of the so-called particle zoo. Experimenters started to see in their accelerator-based experiments primarily new classes of particles with strange lifetimes. There were puzzles related to things like the tau theta puzzle, where there were particles that appeared to have similar quantum numbers, but not necessarily always the same, but similar masses and lifetimes. Some questions about which conservation laws are respected and which are sometimes violated by which force. So today we'll pick up that discussion. We'll talk a little bit about the development of bubble chambers as a primary detector technology in physics. We'll talk about the development of the spark chamber, which enjoyed a moment in the sun in the post-war years. And I'll talk a little bit about neutrino physics and some of the innovations in sort of detector design and data acquisition that came along with the beginnings of this field, which continues to be one of the main driving sort of frontiers of high energy physics research. So near the end of last time's lecture, I showed this picture. This is a nuclear emulsion photo of a so-called spallation event, where a high energy cosmic ray comes into the material and it basically explodes a nucleus. It gives the nucleus enough energy to dissolve into some 20 fragments or so that you see as these different tracks with different specific ionizations coming out. And the most interesting of these tracks is the one heading south from the main interaction point A that's labeled F here with an arrow. What we see here is a nuclear fragment with a high amount of charge. The charge is estimated to be about 5 units of charge because of the very heavy ionization along this track. And then that thing flies here and decays at B. And then from B, we have another few particles coming out, which are labeled with different letters. And the conclusion that the experimenters drew in analyzing this photograph is that the fragment of the original nucleus at F probably contained some kind of unstable baryon, what they would have called at that time a hyperon, or what we would maybe now call a strange baryon, which has a long enough lifetime that this fragment F can live and fly through the emulsion and have its track recorded, but a short enough lifetime that it decays sort of within the time that it takes that nuclear fragment F to slow down, right? It's still sort of flying through the emulsion at the point that it decays at B. And so from images like these, people concluded that there were these strange baryons or hyperons, which had anomalously long lifetimes for such heavy particles, but also clearly could feel the strong force, because you see here the interaction between this hyperon and different nuclei. So it seems that there's some sort of particle which can feel the strong force, but whose decay is governed by something which must be much weaker, because it has a lifetime much longer than we would expect strongly decaying particles to have, right? Particles that decayed via the strong force, we would not expect to have this long decay length that we see here. So as more and more accelerators are coming online, they begin to sort of confirm and to augment the observations from cosmic ray photographs like the one on the previous page. The production cross-section of these new particles is large, as much as a few percent as the production cross-sections for the regular nucleons, neutron and proton, and the pions. And they clearly interact via the strong force because they can form, for example, these exotic nuclei that we saw on the previous page. And it was Murray Gell-Mann who provided the solution. And this is the slide we left off with last time, which was to introduce a new quantum number, which he called strangeness. And the reason for the name is that it was considered strange that these particles could live for so long, despite their large masses, larger than the stable nucleons that we knew about. So this new quantum number strangeness is an additive quantum number. Pions and nucleons, the neutron and the proton, have a strangeness of 0. But the kaons, what today we would call the tau and theta particles, that was the puzzle that we talked about last time, we now call them kaons, have a strangeness of +1. And the hyperons that we saw, for example, in the spallation event on slide 2, have a strangeness of -1. Today we would call them the lambda and the sigma hyperons or baryons. The antiparticles of these therefore have the opposite strangeness. And while the strong and electromagnetic interactions conserve strangeness, weak interactions allow a unit change of strangeness. And since these kaons and hyperons are the lowest energy states containing strangeness, the only way they have to decay down to a state which has no strangeness is to decay via this weak force, which explains their long lifetime. So now what we're going to see is experimentalists putting some new technologies into operation in order to be able to further study the spectroscopy of these strange particles as well as of some other things. And one of the main enabling technologies of this explosion of the particle zoo is the bubble chamber, which was first invented by Glaser in 1952, and it remains a sort of a frontline technology for particle physics from the early 50s until, say, the end of the 1970s, when these extremely large bubble chambers sort of represent the ultimate evolution of the concept, but also the final use of the concept. So in some ways, a bubble chamber is very similar to a cloud chamber in operation. Remember, a cloud chamber we saturate with water vapor, which is basically supercooled by an expansion of the chamber. So we can have an arrangement like we showed in previous slides, where we have some kind of Geiger tube or something else, which is a fast detector. We can put these things, for example, on either side of our cloud chamber. And then when the particle goes through, we can register the pulse on our counters and use that to like automatically expand the chamber. And when we expand the chamber, the ionization trail of particles traveling through the vapor produces nucleation sites for droplets of vapor. The bubble chamber works in kind of a similar way, but with some differences. So the first difference is that we're trying to study now rarer and rarer events. We're no longer interested just in the like interaction of cosmic rays with matter, but we actually want to study rarer processes, for example, like the production and decay of these new strange particles. And so one advantage that the bubble chamber has over the cloud chamber is that we actually use a high pressure liquid instead of a gas. And typically the target is going to be liquid hydrogen. Can somebody tell me what would be an advantage of using liquid hydrogen as a target as opposed to water vapor? Why might we want to do that? It's obviously much more difficult to work with liquid hydrogen than with water vapor. So what advantage would making that change bring us? Think about event rates. I have a beam going into my chamber. What's going to happen when I replace a diffuse vapor with a dense liquid?
Well, won't we just have a higher rate, much higher rate of interaction with proton?
Exactly. So if we're trying to study rare decays, we want to capture as many events as possible. And one way to increase the cross-section for particles to interact with my chamber is to make the chamber much more dense. And so filling it with liquid hydrogen rather than with water vapor gives you, several orders of magnitude change in density. Another difference is that instead of the vapor being super cooled such that the water vapor condenses into droplets after the expansion of the chamber, here the situation is actually the opposite. What we're relying on is for the liquid hydrogen to be superheated such that it wants to boil, but it lacks a sort of nucleation site for the bubbles. And it's, again, the ionization of the tracks going through the material that's going to give the opportunity for these bubbles to nucleate. However, in order for this to work, in order for the trail of the charged particle to leave a track of bubbles, we actually have to expand the chamber before the particles arrive. So the typical operation mode for a bubble chamber is actually to trigger the expansion about 10 milliseconds before the particles arrive. So in the case of like pulsed operation from a particle accelerator, we actually expand the chamber before any interactions happen. And then we allow the bubbles to expand for an additional 2 milliseconds before flashing the photograph. So this is ideally suited for use at accelerators and not really very useful for non-accelerator operations because we have to expand before the beam arrives. So in an asynchronous situation like cosmic rays, there's no way to trigger automatically the readout of the chamber because it has to already be expanding by the time the particles get there. So these are going to be really tightly coupled with the new generation of synchrotrons in terms of experiments, and really only useful for accelerators. Along the same lines as why make the transition from water vapor to liquid hydrogen is also the thing which is pushing these things to become larger and larger over time. So the first examples that we'll talk about were used in the early 50s, and they were typically only a few centimeters in size. So you would have to have this thing, right there where the interaction is happening. Over time, people want to study higher and higher energy interactions. You can have these things in an external magnetic field, but as the energy of the particles gets higher and higher, the typical like radius of curvature of the tracks gets smaller and smaller for the same magnetic field. And again, we want to study rare interactions. For example, some of these things are used to study neutrino physics, where the interactions are incredibly rare, 20 orders of magnitude less than typical nuclear cross-sections. And so this drives the bubble chambers to get bigger and bigger. By the end of the bubble chamber era, you have these truly monstrous ones, which perhaps you've seen if you've been out by the back of Restaurant One at CERN near this microcosm exhibit. You've maybe seen this bubble chamber, which is still sitting out there. This was called the Big European Bubble Chamber that was used mostly in the 1970s, and it had about a 3-meter diameter times 4-meter length. And if you're at Fermilab, you may have been out behind the SciDet building where they have this old bubble chamber, again, from the 1970s. I think it continued to do experiments into the 80s, by which point this technology was pretty much on the way out with a 5-meter diameter. So these are really enormous things. And it takes a fair amount of pressure to keep hydrogen as a liquid. So you're envisioning this really huge volume that has to be incredibly mechanically strong in order to hold in hydrogen under pressure at this kind of a scale. And so the sort of physical challenges in terms of using these things to do experiments get bigger and bigger over time. And you can get an idea of this complexity from looking at some of these mechanical drawings. These are for, I think, the 30-centimeter bubble chamber at CERN, but many of them would look similar. So you need a whole array of services coming in and out. You need some to be connected to some external services to allow the expansion of the gas. You need these condensers to keep things in the liquid form. You need to have portholes in order to enable the photography, and these portholes have to be able to withstand tremendous pressure. So you're using very thick glass that introduces complications about optical distortion of the photographs. As we mentioned before, another drawback is that we have to expand before the event, so it can't really be used in a triggered readout scheme, which really neutralizes some of its advantage in terms of studying rare processes. And safety was a big issue for these detectors. Most notably in 1965 at CEA, one of the French national labs, one of these large bubble chambers exploded due to like a gasket failure, a part of the pressure system. And this explosion is incredibly dangerous because now you're venting hydrogen into an area where you have all kinds of electronics and stuff that's incredibly likely to cause a fire or explosion. And so at the CEA was not the French National Lab, but the Cambridge Accelerator Complex in Boston, where this explosion caused 8 injuries, including 1 death. And so working with bubble chambers was a very dangerous and fraught experience. However, there were some important physics discoveries made using these technologies. One of these was the discovery of antibaryons for the first time. So there were a couple arguments floating around in the physics community why there should be such things as antibaryons. For example, people argued over whether or not there was an antimatter, pair partner to the proton. So there were some arguments in favor, theoretical arguments in favor. We went over in one of the first lectures the story of Dirac's prediction of that the electron, the fermion, should have an antimatter partner based on the wave equation for a relativistic wave equation for electrons that had 2 solutions. There wasn't such a direct prediction of antimatter baryons, but the existence of antimatter fermions sort of motivates the idea that there might be. The neutron has a magnetic moment, which is not 0. And so by some symmetry arguments, people argued there should also be something that's an anti-neutron that would have an opposite magnetic moment. It would be weird if the neutron was its own antiparticle, but it had a non-zero magnetic moment. Not impossible, but it motivated some people to consider the possibility that there should be such things. And there was also a sort of cosmological argument that said that there probably isn't such a thing as antibaryons. The idea being that if there was a lot of antimatter produced in the Big Bang, that we would probably see to this day the signatures of that antimatter annihilating with regular matter, which we know is scattered all over the cosmos. So the lack of seeing this kind of like high energy gamma rays from cosmological sources that would indicate the presence of large collections of antimatter in the cosmos motivated some people to think that there actually aren't antibaryons. There must be some conservation law or physical principle which prevents them from forming. This last argument is still connected to a puzzle that we have. We now know that antibaryons do exist, but that they are not produced in the same number as regular baryons in the Big Bang. And so actually this is still deeply connected to some questions that we have about particle physics even now. But people sought out to answer this question by doing the experiment. Can you produce antibaryons in the lab? And the reaction that they wanted to study was the following one. So if antibaryons do exist, then it doesn't violate any known conservation law to have an interaction of the following type. You can have 2 protons interacting with sufficient center of mass energy that the final state involves 3 protons and 1 antiproton. So electric charge is still conserved here. You have 2 positive charges in the initial state and a net 2 positive charges in the final state. And there's no other like isospin considerations or whatever that should prevent this from happening. And so people started to do the math, figuring out what kind of machine do I need to build if I want to make this reaction happen. And you can do your relativistic kinematics calculations that probably most of you know how to do or have done before. You know the masses of the individual protons are about just about 1 GeV, and so you need to figure out what is the energy that I would need to put into either a fixed target experiment in order to produce this amount of energy to produce two additional particles with the mass of a proton, assuming the mass of the antiproton is the same. And it turns out that the necessary momentum to give one of the initial state protons. So you have a fixed target geometry. You have these protons sitting here in some kind of target, maybe a solid target of some kind that contains protons. And then you bombard it with a beam of energetic protons. Those protons have to have an energy of about 6.5 GeV in order to have enough energy available in the center of mass frame to produce two additional particles of 1 GeV mass. Now, the other strategy that you could imagine here would be a collider to collide two protons from circulating beams. And then the beam energy that would be needed is much less, only about 1 GeV per beam. However, we're still at a point in the development of the field where people don't know how to build colliders yet. We're talking about the 1950s here, and the beam optics in order to be able to steer two beams into collision with an acceptable rate just hasn't been invented yet. So this experiment is going to be done in the fixed target geometry, but I just want to make the point that it's much more efficient energetically to produce new particles from a collider geometry if you have the technology to do that. We'll return to that argument later on when we talk about the first generation of colliders. The main problem in doing this experiment is that it's not so easy actually to convince yourself that what you've produced are actually the antimatter equivalent of protons, because there's another particle which will be copiously produced in these interactions, which also has a negative charge, and that is charged pions. So the reaction that you're trying to produce is this one on the top, where we produce 3 protons and 1 antiproton. But a competing reaction, which looks very similar in most respects and has particles of the same electric charge in the final state, is the one where we just have 2 protons, but a charged pion, a positive charge, and a second charged pion, a negative charge. So if we just, for example, used an analyzing magnet to measure the charges of the particles coming out, it would not be so easy it would not be so easy to convince yourself that what you had actually produced was a antiproton. So can somebody speculate what might be a way that we can build an experiment which will actually tell the difference between a antiproton and a negatively charged pion? So we have a beam of 6.5 GeV going in. It hits a proton at rest in the target, and then we're producing one of these 2 final states. Can somebody give me an example of how we might tell the difference between those 2 final states? John, would you like to take a stab at it?
Yeah, you would expect them to have a different amount of ionization. So maybe you could look at in the bubble chambers, if those have some way of telling the difference in ionization between 2 tracks, you could look at that.
Yes, you would expect them to have a different amount of ionization. So it's true that if we had a sufficiently, if we had a sufficiently detailed ability to tell the ionization per unit length, that we could probably tell the difference between a pion and a proton. For example, if we put this thing in an analyzing magnetic field, you could compare the curvature of the track, which would tell you the momentum of the particle, with the amount of ionization that you observed, and then you could compute whether the available energy was going into producing like a relatively higher momentum pion, which would have a different ionization per unit length, versus a proton, which would be moving slower for the same total amount of energy. However, this is not how the experiment was actually done. Does someone have another idea of what would be different between the top and bottom examples here? Alex, you want to take a guess?
Yeah, maybe if you made the energy of the initial proton low enough to the point where it couldn't produce P plus and P minus, then you could determine how often it decays into the other two.
Yeah, so that's also a really good idea, right? You could do some kind of like threshold of production experiment where you started with a lower energy beam where only this bottom process would be going on, and then you could increase the beam above 6.5 GeV, the critical value, to turn on this second process on the top, and you might observe, for example, an enhancement in the total rate of events that look like this once you moved above the threshold. That's also a very good idea, and that's a way that some particles have been discovered. But actually, the answer in this case is a little bit different than both of those ideas. It has to do with looking at, given that we know the incoming beam energy and that the target proton is at rest, we actually should be able to be sensitive to the momentum difference in the particles which is produced, and compare the expectation of what the outgoing particle momenta should be for protons in the final state versus pions in the final state. And this turns out to be an ideal case for a particle ID system, which is based on DEDX. So kind of combining an element of John's answer with a slightly different detection technology. And that technology is a Cherenkov based particle ID system. So what does that mean? The Cherenkov effect happens when particles move through a medium. So that medium has some index of refraction n, which means that the speed of light in the medium is less than the speed of light in a vacuum, and indeed can be less than the speed with which the particles are passing through. If I'm talking about highly relativistic particles, they're going to be moving close to the speed of light. But if I have some material with a significant index of refraction, what happens is that these particles are sort of moving faster through the material than the electromagnetic disturbances that they produce in the material can propagate. And what we get is the equivalent of a sort of sonic boom in the material for a specific wavelength at a specific angle from the direction of flight. There's constructive interference. You imagine this particle is going through the particle and the material and sort of setting everything vibrating with a bunch of different frequencies, but there's a specific combination of frequency and angle of the Cherenkov cone for which all of this radiation interferes constructively. And what we get is a cone of light of a well-defined opening angle, and that opening angle is related to the travel speed of the particle in the material and the index of refraction of the material. So I can use this effect to build a particle ID system based on the idea that two species of particle which have the same momentum may actually have a different speed, right? So if I have a proton and a pion that are produced with the same momentum, it's difficult to tell them apart by a magnet because they'll have the same radius of curvature. But that momentum is going to result in a much lower speed for the proton than it is for the pion, because much more of the proton's total energy is carried in its rest mass. If we think in non-relativistic terms, right, the momentum is the product of the mass and velocity. So all else being equal, a pion of the same momentum will have a much larger speed to go with its lower mass, and vice versa. So what I can do is I can use an analyzing magnet to select particles of a specific momentum, right? I can put my target in a magnetic field, and then I know that particles of a given momentum are going to curve a certain amount coming out of that target. And I can move, the arm of my spectrometer. I can move my experiment to a specific angle. And based on that angle in the magnetic field, I know what momentum of particles I'm selecting. Then I can drop into that experiment a material with a well-chosen index of refraction such that pions will cause Cherenkov radiation. They'll be traveling faster than the speed of light in the material, but protons will not, because they're traveling slower than the speed of light in the material. And this is the principle behind a Cherenkov particle ID system. Later on, when we talk about more advanced collider experiments, we'll actually use optics to resolve this opening angle, and that gives you a wealth of additional information. But the simplest thing you can do is just choose the material and choose the momentum range such that one of your particles will produce Cherenkov radiation and the other won't. And that's actually how this particular discovery of the antiproton is made. So in this case, they supplied a magnetic field to select particles of about 1.2. They used BeV for billion electron volts in those days. Today, we would say GeV for giga electron volts, but it's the same thing. It turns out that at 1.19 BeV per C of momentum, the proton is traveling at 0.78 C, but the pion is traveling at 0.99 C. So what we want to do is pick a material with an index of refraction such that the pions are traveling faster than the speed of light in the material and will produce Cherenkov radiation, and the protons will be traveling slower than the speed of light in the material and will not produce Cherenkov radiation. So here's a table that I got from Wikipedia, which contains a bunch of different types of materials, and you can see that there's a wide range of different indices of refraction depending on the typical materials that I'm talking about. If I want to discriminate particles with very high momenta traveling very close to the speed of light, then I'll be sensitive to only very small differences in the index of refraction. And in that case, I will probably want to choose a gas as my target, because gases typically have indices of refraction which are very close to 1. They differ from 1 typically by a few parts per million, maybe a few parts per thousand in extreme cases like carbon dioxide. But so for very high momentum discrimination, I can use gases like carbon dioxide or hydrogen or helium gas. Those would be ideal if I want to separate particles which are traveling at, say, like 0.999 C from particles that are traveling at 0.998 C. As I move down more into the regime we're talking about, in order to discriminate between particles which are traveling, say, 0.99 C and 0.7 C, we might want an index of refraction in the range of like 1.3 or 1.2, so that one of those particles produced Cherenkov radiation and the other didn't. And those indices of refraction can typically be obtained with liquid targets. Water itself has a index of refraction of about 1.3, and we can put other liquids in there. If we want to up the index of refraction, we can use hydrocarbons. Benzene, for example, has a relatively high index of refraction at 1.5. The carbon disulfide here is extremely dense, 1.628. That's a very high index of refraction for a liquid. And if I'm in the regime kind of close to water, but I want to monkey around with the exact index of refraction to be sensitive to some particular momentum range, I can mess around with adding stuff to water. The typical thing we do is add sugar to water, which can sort of manipulate the index of refraction of water in the range of like 0.01 to 0.1 above its normal index of refraction of 1.3. So if I add a 10% glucose solution to water, that increases the index of refraction of the water by about 1%, all the way up to a 60% glucose solution in water. That's like quite a that's like a almost close to a candy making or something, where you have really high concentrations of sugar in water. This would make like a simple syrup or something that has an index of refraction which is about 10% higher than water. And then beyond that, if I was interested in really low momentum particles, I could go to the solid regime. So glasses typically have indices of refraction of around 1.5. Then there's more exotic materials like diamond. That would be a very expensive particle ID system, especially in the days before we could produce diamonds industrially. They have indices of refraction well above 2. These would be useful primarily for building a Cherenkov detector with very low momentum particles. Another variation of the same technique is to try to measure the time of flight directly. So instead of relying on a clever choice of materials such that particles of one speed will emit Cherenkov radiation and particles of another speed won't, we can arrange for fast electronics, which will just measure with a high degree of accuracy the time that it takes for the particle to reach our detector. And if these electronics are fast enough, we can distinguish between the different species. This is still the idea that's used, for example, in the timing detector at CMS, right? So we're going to install something which is sensitive to picosecond differences in timing for very highly relativistic particles to tell exactly what path they took through the experiment. But to do this proton-pion discrimination is much less sensitive. Here we're talking about nanoseconds or tenths of a nanosecond resolution needed in order to tell the difference. So here's an example from an experiment where they were looking at antiproton versus meson, here meson meaning pion flight times. So in A, you see the flight time for pions. In B, you see the flight time for antiprotons. And then in C, you have the sort of background that comes from accidental coincidences, which has a more or less flat distribution. So if you can put a gate sort of here to discriminate between case A and case B, you can directly veto, for example, the pion events and let only the proton events through. Then, of course, you'll want to understand something about the background. So these establish a particle which has, so this experiment is done, and they see this peak, which looks like B here, and that establishes that there's a particle with the mass of the proton, and through its bending in the magnetic field, they can also confirm that it has a negative charge. But people would still like to see a more direct proof that the particle is actually the antimatter equivalent of the proton and not some other negatively charged baryon, which just happens to have a mass close to that of the proton. So what's another experiment I could try to do in order to confirm whether these antiprotons are actually antiprotons? What phenomena could I try to look for in my experiment? Let's say I'm going to use a bubble chamber or an emulsion or some massive target like that. What sort of pattern could I look for in those photographs in order to confirm that the particle in question is actually the antiproton and not just a baryon with a similar mass? What happens when I bring matter and antimatter particles of the same species in contact with one another?
They'll annihilate.
Mm-hmm. Exactly. And that's what's shown in this picture here. So having convinced themselves that they are likely producing antiprotons at this Bevatron accelerator, they then put nuclear emulsions into the beamline, and they look for events like this. So you have a what's presumed to be an antiproton coming in from the left-hand side of the picture, and then it produces this star event with multiple pions coming out. And you can confirm that these things are pions by looking at their distinctive, remember, we have this distinctive signature of a pion that it travels through the material losing energy until it comes to a stop, and then it decays at rest as a muon. So you can see a few examples of that, like at 7 here, or at 5 over here, or at 2 over here. These are charged pions coming in and annihilating. And basically they collect statistics of events like this and add up the multiplicity and rest masses of the particles that are coming out, and they're able to convince themselves that this shows a antiproton annihilating with a proton in the material, and that the sort of energies of all of the products coming out are consistent with that hypothesis. This photograph showing one of the early antiproton annihilations is credited to a Mr. Joe Lanuti for help with the analysis of the event. Joe Lanuti is the guy who actually went on to found the particle physics group here at Florida State University later on. So it's of special interest to me. What you start to have with the combination of bubble chambers, other photographic detection techniques, and this new generation of synchrotron accelerators is sort of a physics factory. What is this person doing? This is woman in this picture, and it was almost always a woman. What do you think she's doing with this kind of funky, special table that she has here? What activity do you think she's engaged in here? Anybody have any idea what she's getting ready to do? So this is a specialized table used for the analysis of bubble chamber photographs. And you see that there's a roll of film over here. And then there's this sort of projector thing over the top. And then she's got some like measuring devices available to her down here on the table. So what happens here is that film from bubble chamber photographs is developed en masse. Some of these experiments are taking literally millions of photographs. And then each of those photographs needs to be digitized by hand. And the way that's done is by people like what this woman is doing. You sit at this special table, you click on to the next photograph, and it will project onto the table the bubble chamber photograph that you're currently analyzing. And then you can kind of move these measurement apparatuses. You see she has some controls here for like advancing the film next to her hand. And then she has like literally protractors and rulers that she can move around on this table and measure things like the length of tracks, the curvature of tracks, the angle between tracks. And all of that is then entered onto punch cards as the digital record of the event. And so it becomes this sort of industrial scale thing to find the person power, the specialized optical equipment, and then ultimately the computer time to convert each of these photographs into a set of numbers that can be digitized, and then the analysis can be run on the computer. And as you can imagine, this is quite a large scale activity. If you're talking about millions of anything, even if it only took her 1 second to digitize a photo, that would already be a huge effort. But of course, it takes much more than 1 second. And so people started to try to optimize the running of this so-called physics factory to maximize the output of, for example, the bubble chamber at the Bevatron. And one of the techniques that they used to do this was something called operations analysis. This is a plot from the Alvarez group at Berkeley that was analyzing bubble chamber photographs, discovering new particles. And what problem that the group is trying to solve by this style of analysis is to figure out how can they make this physics factory function more efficiently. So you see they have different scanners. Each of these initials is a person, right, who has a different rate of scanning. You can see that the events per hour that a scanner can digitize ranges from a high of maybe 13 events per hour. So that's like 4 or 5 minutes per photo, not very fast. And some people are less than half as productive. So people can be scored in terms of their deviations from the average performance, just like a worker on the sort of factory floor of Toyota or something might be scored for the number of components they're like adding to the chassis as the car rolls down the line. And then you can also think in terms of like inputs and outputs. Like, let's say that I have an extra $10,000 to spend on the experiment. Should I spend that on improving the bubble chamber in some way, or will I get a better output if I just add another scanner to the team so that I can capture more film and analyze it in the same amount of time? So people start to do things like calculate the partial derivative with respect to the total number of photographs analyzed of different inputs in order to figure out like where, if I have additional resources to put in the experiment, where should they go in order to maximize the physics output. And any of you who have seen the sort of quantitative case for a specific project to be funded will sort of maybe understand that this style of analysis is still very much with us. As soon as you have these big, complicated experiments with lots of moving parts and lots of people, the question of like, where can I inject resources to do the most good becomes a really critical one. And this whole field is called operations analysis, and it's really something which was developed during the Second World War for military purposes in order to optimize the war effort. Blackett, who we saw, was a top physicist in the UK who made several discoveries using cloud chambers starting from before the war. He pioneered this field during the Battle of Britain when the Nazis were like flying planes over Britain to bomb it, supposedly in preparation for an eventual invasion. Blackett took on the task of optimizing the number of anti-aircraft rounds it would take to shoot down a German plane. So by sort of changing who got the ammunition and what kind of weapon it was assigned to and stuff, he was able to decrease the average number of rounds needed to shoot down a single German plane from 20,000 down to 4,000. And this success early in the war spawned this whole field of operations analysis, which is still with us in many like industrial contexts. You can see here that the computer time used per event is also tracked, right? So the number of seconds that it takes for the analysis to run on the event once digitized is also being optimized. You can see it's 73 seconds per event in 1962, and by the end of this plot in 1966, they've got it down to 54 seconds. You can calculate different things doing this kind of analysis. At the time that this plot was made, the Alvarez group is doing 1 million events per year. The group-specific rate, which he calculates as the number of photographs analyzed divided by all the people on the team, so not just the scanners, but also the experimentalists and technicians, is only 5 per hour. And so you can see that even though the individual scanner might be able to achieve a rate in excess of 10 per hour, the scanners are still like half or less of the total team because the group specific rate is 5 per hour. That means that for every scanner, there's at least one other person working somewhere in the group to collect these million photographs. So it's just interesting to see people starting to think in these terms of really like industrial organization and management techniques already by the 60s. People tried to speed this up by inventing sort of machines to assist the operator with the measurements in a partially automated way. This is a machine called the Frankenstein, invented, I think, by a guy named Frank, hence the name. But the idea is that there's some algorithms built into this thing so that the operator is just measuring like specific points on the picture according to some procedure which they've learned, and then the computer is assisting with calculations of like the sagitta of a track or whatever, so that the operator can move more quickly and digitize things faster. So this is sort of the debut of like a cyborg style of analysis that is still basically how we do analysis today. I mean, we're no longer measuring photographs, but I venture that there are very few people in this room who have ever done a physics analysis without a computer. And this starts to be the case already in the 60s. So it's basically a cyborg team of a computer and a person measuring the events and inputting the data for later analysis. So the whole name of the game here is to do a huge reduction in the amount of data from photographs, which have a huge amount of data associated with them, down to individual kinematic quantities, which are relatively few bits. So a black and white photo of the kind of resolutions we're talking about might be 10 to the 7th bits, something like that, to hold a photo at the full resolution in memory, which computers at the time are completely incapable of doing. But if you can measure the individual tracks, and there's, let's say, 10 tracks, and each track has a few parameters associated with it, each of which is a number that you hold at like a fixed precision, you might be able to reduce the original photograph. To digitize that fully would be 10 to the 7th bits, impossible for computers at the time. But to pick out 10 interesting tracks and measure their main parameters and input that might only be 1,000 or 10,000 bits, which is something that the computers of the time could do. This is a picture from a training film. Basically, they had pre-digested events for possible new additions to the scanning team to analyze, and then you could measure their performance to see if they were worthy of being added to the group. If the operations analysis told you that what you needed was another scanner, then you could train them using these kind of industrial style training techniques. Another interesting thing that the Alvarez group popularized during this time was the idea of the look elsewhere effect. Can anybody summarize for me what is the look elsewhere effect and why somebody that was doing these analyses might be worried about it? Who knows this term, the look elsewhere effect? John?
Is it something along the lines of like the idea that if you're analyzing a large amount of data, you can still see, you expect to see some amount of statistical excesses, even if they're not actually like interesting features of the data?
Yeah, exactly. So we're talking about millions of events being processed per year. So there's many different histograms you could make, right? You could make it very massive 2 tracks, a very massive 3 tracks, whatever. And then for each of those histograms that you could make, there's like many different subsamples that you could make them for, right? Maybe the accelerator runs a few days every week and then it has some shutdown or something. And so if you bin the data by the week that it was collected and make this whole multiplicity of histograms, even if there are absolutely no new particles in the underlying data, you should still expect some base rate of statistical fluctuations giving rise to apparent peaks in the data, just because you've sliced and diced the data into so many different bins on so many different histograms and so many different channels. And people, even back in the 60s, people were smart. They didn't have the full array of statistical tools that we would use now to calculate the look elsewhere effect. By now, there's a well-defined procedure for changing like a local significance into a peak, into a global significance, given the number of events you have and the number of plots in your analysis. But people knew even back then that this could be a problem. And so the Alvarez group wrote this program called Fake, later a program called Game. And the way that they evaluated the look elsewhere effect was kind of cool. Like they basically had these programs generate fake data sets, and then they would plot these fake data sets next to the real data sets, but without labeling which was which. And then they would put plots like these up on a bulletin board in the lab, and the physicists would take turns like circling which of the histograms they thought corresponded to a real particle discovery. And then you could look and see like which particles were actually, which plots were actually real and which were pseudo data. And you could sort of quantitatively evaluate the likelihood that the human brain would pick the wrong fake fluctuation as opposed to an actual particle. And you could then downgrade the significance of the results that you did see according to this factor. So rather a clever way of evaluating the look elsewhere effect in a sort of empirical way, even before the full statistical formalism was well developed. Kind of a clever idea. anyways, so to end this part of the story, this is a picture of one of those anti-proton events at the Bevatron bubble chamber. By now they have this 72-inch bubble chamber, which is able to make very high resolution photographs like this one. Here is an event where you have a PP bar going to a lambda and a lambda bar, and then the lambda decays to a proton and a pi minus. And then the anti-proton from that lambda bar decay annihilates at the upper left and creates some additional tracks. So the initial particle is coming in from the bottom. You're producing a pair of these strange hyperons, which are electrically neutral. So you don't see the tracks from those, but then you have tracks starting here and here, which are the decays of the lambda and the lambda bar specifically. And then basically with these synchrotrons and these bubble chambers and the ability to digitize so many photographs per year and extract the track parameters and then make like invariant mass plots, you start to discover lots and lots and lots of new particles, the so-called particle zoo. And ironically, one of the reactions of the people who were doing this work at the time to all the particles that they were discovering was initially excitement, but it quickly turned to disenchantment. People around this time coined the phrase Berkeleyitis to describe the feeling of alienation that a experimentalist has from his or her data when the scale becomes like too large for the human mind to comprehend. And this sort of disconnection of the experimenter from the experiment, because there's too many mediating layers in between them and the apparatus, or between the apparatus and the final analysis, I would argue we still struggle with solving this problem. One technology that was seen as a possible salvation for the field was called the spark chamber. Experiments, there was a breed of experimenters around this time, like late 60s, early 70s, who said, if we could just get back to using fully electronic detectors without all of this film and all these millions of pictures and all of these scanners digitizing, then the data could go directly from the experiment into the experimenter's hands without all of these layers in between. And we could return to the days of small teams, which understood the experiment well and were doing the final analysis. I will leave it as an exercise to the reader if our current generation of fully electronic detectors have indeed realized this dream. Anyways, I'm going to pick up the story of the discovery of the standard model along this dimension of accelerators in a bit. But first, I wanted to take another path and talk to you a bit about neutrino physics, where another set of technologies that will prove really important to the story are being developed. So one of those technologies that's going to be important to the development of neutrino physics in the post-war years is the technology of scintillators. Scintillators are, broadly speaking, materials that give off light, visible or ultraviolet light, typically when charged particles pass through. And they're broadly can be separated into two categories. There's organic scintillators, which are based on various hydrocarbons. And then there are inorganic scintillators, which are typically crystals. The main principle behind organic scintillation is that in all kinds of different organic molecules and all kinds of different hydrocarbons, you have these different types of bonds between carbon atoms, and then bonds between carbon atoms and the hydrogen, which kind of hang off of the main skeleton of the molecule, which is made out of carbon atoms. And I'm not going to go into all the details about the organic chemistry here. We're going to talk more about scintillators later on. But I just wanted to give you a kind of flavor for how scintillation works in order to motivate its use in some of the discoveries in neutrino physics that I want to talk about. So let's just suffice it to say that organic molecules are extremely complicated, right? Organic chemistry is its own whole field with lots of interesting topics to discuss and lots of interesting results having to do with the structure of these things and how we can design different hydrocarbons to do different jobs and to have different physical properties. But one of the physical properties that a lot of hydrocarbons have is that it turns out that in this super complicated electronic configuration of these like rings and chains of carbon, you can basically choose materials which have some really desirable properties as scintillators. So the main problem with designing a scintillator, using a scintillating material in a particle physics experiment, is that a typical material which has like an energy level that can be excited by charged particles passing through, the material will absorb that same frequency of radiation that will be produced by that transition. In order to have a scintillating material which is effective for use in an experiment, we want to induce what is known as a Stokes shift. And that's basically a shift between the probability of absorption versus emission as a function of the wavelength. And the complex electronic structure of organic molecules gives plenty of opportunities for these kinds of shifts to emerge. So it turns out that in certain organic molecules, the most likely transitions for absorption of energy from ionizing radiation passing through, as contrasted with the most likely decays of these excited states, is a little bit different. And the ways in which they differ are just kind of down to specific differences in the chemistry of the different materials that you choose. But it turns out that there are organic materials which are pretty strong scintillators in the sense that they produce a lot of photons per unit energy that's deposited in them. And they also display this Stokes shift. That is, that the probability of absorption versus the probability of emission are separated from one another by various effects happening in the material. And that makes it a good material for doing experiments, because the light that is produced, instead of being immediately resorbed by the next molecule in the line, will propagate for quite a distance before being absorbed. And a lot of these materials are plastics. And plastics are a fantastic material to build experiments out of. Plastics are relatively cheap to manufacture. Various processes, casting, extrusion, injection molding, can be used to shape plastics into sort of arbitrarily complex shapes, right? If you can make a G.I. Joe figurine in like whatever shape and size you want, you can also make a plastic scintillating detector in any size and shape you want using widely available industrial technologies. And so plastic scintillators are really a key technology in physics. And we still use them a lot. We use them in CMS, we use them in Atlas. They're just very good materials from a lot of different perspectives. They do have some drawbacks and vulnerabilities. In particular, they're hydrocarbons, so they like to catch on fire. And when they burn plastics, I don't know if any of you have been unfortunate to be next to a fire that somebody threw some plastic into, but it produces really noxious chemicals when it burns, and it can be really difficult material to deal with for like firefighters or whatever. So we have to pay some attention in deploying them in our experiments, that we're not creating a huge fire risk that's going to get a lot of people hurt. But with that as one of the main drawbacks, these are really fantastic materials for particle physics. The typical way that a scintillator detector is made is by taking some base material, which is usually either polystyrene, which is the same material that's in a lot of other plastic manufactured goods. It's very easy to make and mold and shape. The inputs are not very expensive. These things basically just come from oil. Then you put one or more agents or fluors into the material in order to help induce an even greater Stokes shift than would occur in the material naturally. So we will typically have the base scintillator, which will be polystyrene, or the other plastic that's commonly used is polyvinyl toluene, or PVT. Then we'll have a primary agent. So that by itself can be a scintillator. It does produce some light. Then we add to the equation a primary additive, which is also a scintillator, maybe a stronger scintillator that gives more photons in the desired wavelength range per unit energy. And then a secondary fluor or agent, or sometimes called a wavelength shifter, whose main job is to absorb the emission photons of the primary additive and re-emit them at yet another wavelength, so that the propagation distance of photons in the material is even higher. And so you can basically design your own scintillator by choosing the appropriate base material depending on your application. This can include also liquids, although most of these liquids are not very pleasant to be around. And then you add a primary agent and often a secondary agent to sort of play with the absorption and emission peaks and get them into the desired spectrum of wavelengths. So this is a super powerful technology. Not only can the plastic be physically molded and machined into all kinds of different shapes, but by cleverly choosing the primary and secondary additives, you can also have some degree of control over things like the emission wavelengths, the absorption wavelengths, and the attenuation length of light inside the material. So many of these different combinations may be used depending on your specific use case and the limitations that you have in your particular experiment. And we'll return to all this when we talk, for example, about calorimeters in collider experiments, but I just wanted to sort of give you a flavor of it. Then typically what you will do is have some kind of plane or plate of scintillator that's large in area and that has a good acceptance for particles coming through in any part of it. Sometimes you will then machine a channel into this thing and put what's called a wavelength shifting fiber. So this would be like a second piece of plastic distinct from the first that has like particularly these secondary agents or wavelength shifters inside. So the main idea is that the light is produced in the bulk of this material. Some of the photons fall into these scintillating fibers, and these wavelength shifting fibers have a much longer mean-free path for photons of that wavelength, and they essentially act as guides to extract the light and bring it out to a photodetector, about which more in a few minutes. And then when you have this photodetector, then you're going to couple it to some kind of electronic readout system, which is basically detecting a current pulse from the photodetector, and usually in modern experiments, sending it to some kind of chip that digitizes it. Although in the early days of the experiments, people would have just attached these things to electronic counters directly and then been able to do logic coincidences and anti-coincidences, etc. There's another class of materials, which I won't talk about too much now, but which will again become important when we get to collider experiments. Those are inorganic scintillators. The chemistry of what happens here and I should say the physics of what happens as far as the generation of light in these materials is even more complex with lots of competing processes, but these can be preferred to organic scintillators largely due to their faster speed typically of the process to get the photons out, and they're typically a lot more dense than hydrocarbons. And so especially in electromagnetic calorimetry, where we have relatively compact showers, these would be a good material of choice. I'm not going to belabor this, but just to preview what we'll talk about a little bit more later. And then, of course, we need to have some kind of way of detecting the scintillation light. And then in experiments at that time, until fairly recently, this was almost always something called a photomultiplier tube. So the idea of the photomultiplier tube is that it has a bunch of stages of gain so that we can have a very low intensity light source, sometimes just a single photon. If you imagine that you have a large volume with some attenuation length, the number of photons which may reach your photodetector may be in the single digits or maybe only one, depending on the use case. And the idea is that by having successive amplification stages, so there's basically a high voltage applied to this whole tube, and then in between each of these dinodes, intermediate stages of amplification, there's a voltage dropping resistor such that there's like a chain of decreasing voltage as you go through this thing. So electrons which are produced in the initial photocathode are attracted to this first dynode. And then when they fall onto that, they have enough energy to liberate some additional electrons. And those are then pulled towards the second dynode, where each of them undergoes a successive multiplication, et cetera, et cetera. So from an initial just single photon coming in, you can produce a macroscopic current coming out by having these multiple stages of amplification. The material of your photocathode, so that's basically the metal that gives up an electron by like the photoelectric effect when it falls onto the metal. You can choose that to be sensitive to different wavelengths of light. And then you can also choose the material that the window is made of to be sensitive to different wavelengths of light and block other wavelengths. And this is useful, for example, if you have very small signals, but they're like in the ultraviolet versus some kind of background, which is like visible spectrum light, which is leaking into your experiment. You can, to some extent, choose which wavelengths you want the photomultiplier tube to be sensitive to by the choices of the materials that you use. One of the downsides of this arrangement, so you have a lot of kind of slow electrons floating through this volume. And in order for the amplification to actually work, they need to be able to successfully get to the next stage of the amplification. And a magnetic field can really screw this up, right? You imagine that if you fall into this thing and then the electrons don't have that much energy, they may just end up looping inside a magnetic field here rather than making it all the way to the next dynode. And we typically do have magnetic fields in high energy experiments. In fact, any photomultiplier tube is likely around some kind of like electronics, which is likely to have some fringe fields. And these things are very sensitive. So you use sheaths made of what's called a mu metal. This is a special alloy, which is typically mostly nickel with some amount of iron, molybdenum, and some other impurities added to it. And basically, this is a metal which has a very high permeability to magnetic fields. That is to say that magnetic field lines will prefer to pass through this metal as opposed to the photomultiplier tube that it's shielding. So you place this thing inside of one of these mu metal shields, and that will largely protect it from external magnetic fields. These are kind of going out of fashion in physics now. Other photodetectors, silicon-based photodetectors, which have basically one amplification stage, which is microscopic instead of these large macroscopic arrangements, have a lot of advantages. I won't talk about that now, but we will revisit it later. So those are some of the technologies which are being developed to do neutrino physics. And I just want to remind you about the physics application that people were interested in. So it was known already in the mid-30s or so that beta decay gave off electrons with a range of energies, not just one energy. So if you look at like a gamma emitter, typically that's like a delta function of gamma rays coming out of it. Or maybe there are several discrete transitions in the nucleus which each emit gamma rays, and you can do a spectroscopy and see that there's multiple sharp peaks. But beta rays, which are electrons coming out of the nucleus, do not show this pattern. They have a smooth, continuous distribution of energies. And this is difficult to explain if your model of radioactive decay involves fixed energy levels of the nucleus. So in the 30s, Pauli initially introduced, and then Fermi sort of ran with and expanded this concept of a hypothetical neutrino, which is a light neutral particle that carries the rest of the energy away. Fermi writes down the so-called Fermi theory of beta decay. He wrote it down and submitted it to the journal Nature, which rejected it because it, quote, contains speculations too remote from reality to be of interest to the reader. But it should have been of interest to the reader because it turns out to be true. People were able to then observe the recoil of the nucleus in cloud chamber experiments that provided evidence for the Fermi theory, that basically if you add up the nuclear recoil and the kinetic energy of the beta particle itself, you can find basically the missing energy, which is attributable to the neutrino escaping. So people started to get ideas in their head, how could we directly measure these neutrinos instead of just inferring their existence? And the first people to really successfully do that were this team led by Cowan and Rains, which they called Project Poltergeist, since these neutrinos are kind of like ghosts. Their insight was that you could arrange things such that there would be a time coincidence of two different signals coming from a process known as inverse beta decay. So Fermi's theory predicts that there should be something called inverse beta decay. That's where neutrinos enter your material, and occasionally what can happen is that one of those neutrinos will be absorbed by the material. Instead of the normal beta emission where you have an electron and a neutrino coming out, you can have a neutrino go in and then a positron come out. This positron will then like wander through the material, losing energy until it is captured in an annihilation event with another electron in the material. So electron-positron annihilation at rest will give rise to a distinctive signal of two back-to-back gamma rays, each of 511 keV. That's the mass of the electron. So there were two such masses in the initial state. It produces two back-to-back photons in the final state with this well-known energy. And then the other product of this inverse beta decay is that a neutron is plopped out of the nucleus and goes floating through the material. And Cowan and Raines realized that if they put another material in the target, which had a tendency to capture those neutrons, then they could manufacture a third gamma ray with some time delay relative to the initial ones from electron-positron annihilation. So inverse beta decay happens, neutrino goes in, positron comes out and annihilates, giving rise to some gamma rays. This happens relatively promptly. And then a neutron comes out, which is kind of slow, that bumps around in the material for a while until it finds a nucleus that can absorb it. Cadmium is one such nucleus, and cadmium has the nice property that when it absorbs a neutron, it goes to an excited state and then emits its own gamma ray. So there's a distinctive signature of these two gamma rays in coincidence, then some time, and then a third gamma ray. And this is the signature that Cowan and Raines built their experiment to detect. So their idea was to fill a tank with water, dope this water with cadmium in order to provide that third gamma ray, and then surround the volume with photomultiplier tubes that would be sensitive to the individual gamma events. So these gammas then shower in the material. Sorry, these gammas can then excite other water molecules and result in some visible light reaching the photodetectors. And so they have their photomultiplier tubes connected to a circuit which looks for a coincidence, then some time, then a third gamma ray. Excuse me. They did this experiment, their initial idea was actually to use a nuclear weapon as the source of the neutrinos. So they had a proposal to the AEC. Sorry about that. They had a proposal into the AEC to blow up a nuclear weapon next to their detector as part of like ongoing tests in the desert in the Southwest. But of course, that's kind of an expensive way to provide some neutrinos. It turns out that it's a better way is to put your experiment next to a reactor. So they first started out at the Hanford site in Washington, which was part of the Manhattan Project, and then continued to produce material for bombs after the war. They did an initial version of the experiment there and then moved it to the Savannah River reactor complex in South Carolina, where there were some reactors that they could basically measure the difference in the rate of these triple coincidences with the reactor on versus the reactor off. And if they saw an excess of events when the reactor was on relative to when the reactor was off, that would be strong evidence that they were capturing neutrinos from the reactor and producing these triple coincidences. So that's what they did. In 1953 at Hanford, they got a 2 sigma result. Then they moved the whole thing to Savannah River and ran in 1955 and 56, which confirmed their results at a high level of significance. So this is considered to be the direct observation of the neutrino. Another detector technology that was being brought into operation at this time was the spark chamber. This is pretty conceptually simple, although it's difficult to get it working well in practice. The idea is that you have a bunch of alternating plates, which are held at high voltage with respect to one another. This creates a strong electric field in the region between the plates, which, much like the Geiger tube, will produce amplification and avalanche of electrons when a charged particle goes through. So the idea is you can put like scintillator paddles on the top and bottom. So this would be like a flat sheet of plastic scintillator of large area, of the same area as the like cross-sectional area of these plates. And then another one on the bottom, and you build a coincidence circuit such that when those two fire at the same time, indicating that a particle went through, you have a capacitor in the electronics, which is held at a very high voltage, like typically 10 to 20 kilovolts. And when you see a scintillator coincidence, you discharge this capacitor onto the plates. So you briefly charge up the plates to this huge voltage. And then just like for the Geiger tube, the ions which were produced by the passage of the charged particle form a path for amplification to occur. And then you can fill this with a gas, which will give actually visible light when one of these little mini lightning bolts kind of goes through. Typically, you're using mixture of helium and neon gas for its properties. And so the sparks are usually a violet red color as shown in this picture. By placing cameras around this thing that can be triggered by the same coincidence of the scintillators, you can photograph the arrangement of these sparks from multiple angles. And from those photographs, you can then reproduce the three-dimensional trajectory of the particle. Even more cleverly, some experiments instead of cameras used microphones. So every time you have one of these sparks, there's like a little thunder clap in your experiment, basically. And by having like two or more microphones like around the edges of the plates, you can actually time the arrival of those little thunderclaps and reckon where the particle passed through. And this would give you a completely digital or a completely electronic, not digital, but a completely electronic readout system, which doesn't involve any photographic film at all. The sort of dream that we talked about a few slides ago of getting away from the need to analyze millions of photographic films in order to make a technology that can detect rare events. So armed with this spark chamber, we can imagine a search for rare events in a much more efficient way than analyzing so much film. Again, the bubble chamber cannot be used in a triggered way because it has to be expanded before the particles arrive. But the spark chamber is perfect for use in a triggered system. And that's exactly what Lederman, Steinberger, and Schwartz will do in 1962 in order to discover the second generation neutrino, the muon neutrino, or as people called it at the time, the Neutrino, which I kind of wish we had stuck with this name. Sounds like a coffee flavor or something to me. People already started hypothesizing in the 1940s when the muon was discovered that if there's a neutrino which is closely related to the electron in the sense of being involved in beta decay alongside the electron, the existence of the muon implies that there may be also a muon form of the neutrino. Sakata and Takeshi, two Japanese physicists, predicted already in 1942 that there was a two meson theory and that each meson had its own neutrino associated with it. So this experiment was built in 1962 at Brookhaven National Lab. This started with a proton source from a synchrotron called the alternating gradient synchrotron, which was operating at Brookhaven at the time. It produced a beam of 15 GeV protons, and those protons could be fired onto a target. The target was made of beryllium for nuclear physics reasons. This was a good target material. And this protons falling onto the beryllium target produce a lot of secondary particles, but some of them are pions. These pions fly through space and then they decay in flight into a muon and a muon antineutrino or a anti-muon and a muon neutrino, depending on the flavor of the pion. And then basically you can put a bunch of shielding material between the target and your experiment to screen out any particles other than neutrinos, right? Even neutral mesons and baryons will not make it through all this shielding. This was 2,000 tons of armor plates from old surplus naval vessels. And actually putting together this much absorber was a big part of the effort in order to be able to do the experiment. But you see there's all this steel in between the interaction point and the experiment, and it's absorbing everything except the neutrinos. Then in the actual experiment area, you put this detector, which is made of alternating scintillator planes to trigger the spark chamber readout. Those are labeled A. These big white boxes are the spark chambers themselves. And then there are some veto counters around B, C, and D, which are to reject either through-going showers from cosmic rays or from like punch through of the particles from the beam. And what you're left with should be a reasonably pure sample of the only thing making it through our neutrinos. And then you can compare, for example, the rate of the neutrinos going through the experiment with the machine on versus off. You can play games with like adding or subtracting shielding to try to estimate the amount of punch through which is happening and basically count the number of events under these different scenarios. So most neutrinos are going to pass through the detector without interacting, but once in a great while, there will be a muon neutrino which comes in here, interacts with the material, and gives rise to a single muon whose trajectory you can then see through these spark chambers. And that's exactly what they saw. So neutrino goes in, it produces a muon inside the spark chambers. You see here a picture of Schwartz standing in front of, I think this is a representation of the spark chamber. I don't think this is an actual event going through at the same time that they flashed the photo, but I could be wrong. You see they have little counters here that would like flash if it's a cosmic ray. I think he's standing in front of the one that would flash for a single muon event, but that's what they would really care about. Not a big bunch of tracks coming through as a shower, as you see here, but just one single track, which starts somewhere in the middle. That's the smoking gun that a muon neutrino interacted and gave rise to a single muon. They were able to calculate using the theory what the energy spectrum of the neutrino should be based on the spectrum of pions coming off the beryllium target. And they saw a clear signal in terms of the amount of events that they saw with the beam on hitting their target versus a couple of different background runs with lower intensities in the machine. And the number of events that they saw in the quote unquote normal runs where they're looking for these single muon events is 56 over a background basically of 5. And so this is a very clear discovery of the muon neutrinos done using this new technology of the spark chamber. The spark chamber is not going to last very long as a frontline technology. It will soon be supplanted by electronic detectors of greater sophistication with somewhat easier requirements, which we'll talk about next time. But the idea of the spark chamber, the idea that we should, instead of trying to produce reams and reams of photographic film, instead put our energy into arranging electronic detectors spatially, which allow us to directly extract the information that we're interested in, rather than putting it onto photographic film. That tradition is still very much alive, and in the next lecture, we'll see some more examples of it. We have time maybe for a quick question if there is one before we end for today. Are there any questions?
I had a quick question. You said that bubble chambers couldn't be used in a triggered way because they had to be expanded before the particles could come. But I'm wondering, why does that stop them from being used in a triggered way? Like, why couldn't you just start expanding them when you wanted to trigger them? Would it just take too long?
Well, because the event that you're trying, so when I talk about triggered, I mean, of course, it can be triggered in the simplistic sense of like, oh, I'm expecting a pulse from the accelerator. I'm going to expand the chamber, so I'm ready for it. I mean, that's exactly how they were used. But normally, when I talk about triggering, it means like to distinguish like a class of events that I am interested in from a class of events that I'm not interested in. And there's simply no way of getting the information out of the bubble chamber in order to make that distinction, because I have to expand the chamber before the particles arrive in order for the liquid to be superheated so that the bubbles can be produced, right? So I have to decide to expand before the event happened. That means my decision can't be based on anything in the event.
Okay, thanks. That clears up my confusion. Thank you.
All right. Well, I propose that we stop here for today. I've finally, I think, caught up with where I wanted to be. And so next time we'll be on to new topics. Thanks, everybody. Bye.
Thank you.
Yeah.